Ever try to, like, fix a cracked phone screen with a hammer?
Yeah, me neither.
Seems a little counterintuitive, right?
Well, get ready for kind of a wild ride today because we are diving deep into the world of ordered defect compounds.
Which is where, believe it or not, scientists are adding defects to materials to, get this, make electronics perform better.
It really does kind of flip our thinking about semiconductors on its head.
Typically, we think of defects as like the enemy, right?
Right.
They mess with the smooth flow of electricity and limit how efficient devices can be.
Yeah, it's like trying to drive a sports car through a construction zone.
Not exactly a recipe for speed.
Right.
But here's the twist with this.
Instead of fearing these defects, researchers are figuring out how to, control them.
Even leverage them to our advantage.
They're working with a compound called QN5SE8.
Okay.
And the cool thing is it can handle a bunch of defects without breaking a sweat.
It's like, imagine a perfectly arranged game of Tetris. But instead of blocks, you have these atomic vacancies and misplaced atoms, and they're all lining up in predictable patterns.
And these organized clusters, or what we call electrically benign complexes, they don't get in the way of electron flow like their random counterparts would.
So instead of causing chaos, these defects are like forming their own little orderly society within the material. And here's where it gets really interesting. The research shows that these ordered defects can actually enhance performance.
Wait, hold on. So defects making things better?
How did they even discover this?
They created thin films of QN5C8 using a special solution-based method.
Kind of like carefully layering the ingredients for a high-tech cake.
Okay.
Then they built transistors with this material and compared them to traditional ones.
All right, I'm on the edge of my seat. Did these defect-powered transistors pass the test?
They aced it.
They demonstrated significantly higher carrier mobility. Think of it like this. Electrons were cruising through this material like it was the Autobahn, no traffic jams in sight.
That translates to blazing fast speeds for your devices.
So we're talking about phones that can, download a whole movie in seconds, all thanks to some well-behaved defects. Sign me up.
What else did they find?
They also observed a sharper sub-threshold swing. Now, bear with me for a second.
Okay.
Imagine flipping a light switch. You want it to respond instantly, right?
Right.
That's what a sharper sub-threshold swing does.
It allows these transistors to switch between on and off states with incredible efficiency, saving energy and boosting speed.
In their tests, these ordered defect transistors had a sub-threshold swing down to 135 millivolts per decade compared to 440 for traditional materials. A remarkable difference.
Wow. Okay. So not only are these electrons moving faster, but they're also, switching gears with incredible precision.
This is starting to sound like a recipe for some seriously powerful electronics.
And we're just scratching the surface.
This discovery isn't just about speed and efficiency. It could revolutionize how we manufacture electronics.
Remember that solution-based method they use?
Yeah.
That translates to a potentially simpler, more scalable, and cost-effective production process compared to traditional methods.
Hold on, cheaper and more efficient.
Now we're talking about a potential game changer for everything from our smartphones and laptops to maybe even electric cars and beyond.
This is huge. But before we dive into all the exciting applications, let's take a quick pause.
We'll be right back to unpack the why should I care part of this revolutionary technology. Don't go anywhere.
And we're back.
We've been exploring this fascinating world of ordered defect compounds.
Where these imperfections might be the key to unlocking, the next generation of electronics.
Right.
Before we pause, we were about to kind of dive into the why should I care part of all this.
So the researchers didn't stop at just making better transistors.
They actually used QN5SE8 to create some pretty impressive devices, demonstrating the real-world potential of this technology.
Okay, I love a good sequel. What did they create?
They built 3D complementary inverters.
Which are essential components for complex electronics.
Right.
Picture them stacking these QN5Z8 transistors with carbon nanotube transistors.
Okay.
Building upwards to create a three-dimensional structure.
So instead of spreading everything out on a flat circuit board, they're going vertical.
Exactly.
Like building a high-tech skyscraper instead of a single-story building.
Yeah, and this 3D approach allows for much greater density.
Packing more functionality into a smaller space.
Right.
Plus, these 3D inverters demonstrated faster switching speeds and lower power consumption compared to their 2D counterparts.
That's what I'm talking about. More power in a smaller package, all thanks to these carefully orchestrated defects. What else? Don't hold back on the good stuff.
They didn't stop there. They also created high-resolution micro-LED displays driven by arrays of these QN5C8 transistors.
Okay, now things are getting really interesting. Are we talking about, like, screens so sharp they could make a diamond jealous?
Imagine displays with pixel densities greater than 500 pixels per inch. That's incredibly sharp.
Wow.
And they achieved all of this while keeping the fabrication process below 400 degrees Celsius.
Hold on. Why is the temperature so important? Is there, like, a danger zone temperature where electronics, like, start to melt or something?
You're on the right track. Traditional electronics manufacturing often involves really high temperatures.
Which can drive up costs and limit the materials you can use.
Right.
The fact that they can create these high-performance devices at lower temperatures is a big win for scalability and cost-effectiveness.
So we've got speed, we've got efficiency, we've got lower production costs, and we've got stunning displays.
It's almost too good to be true. But, I mean, there has to be some challenges, right?
It can't all be smooth sailing in the world of, cutting-edge electronics.
You're right. There are always hurdles to overcome.
While the performance they've achieved is exciting, long-term stability and reliability are still areas of active research. They're exploring ways to improve the interface between the semiconductor material and the dielectric material, as well as increase material purity to address these challenges.
So, like any good relationship, it's about finding that perfect balance, making sure these defect-powered devices can go the distance. What about other materials?
Is QN5C8 the only, star of the show?
That's the really exciting part.
While this research focused on QN5C8, the researchers believe this approach could be applied to other materials as well. There's a whole universe of potential ordered defect compounds out there waiting to be explored.
A whole universe of possibilities. That's what I love about science, always pushing the boundaries of what we thought was possible.
So while this technology is still kind of in its early stages, it sounds like we should be keeping a close eye on it. It has the potential to be, absolutely groundbreaking.
It does.
Anything else we should know before we kind of wrap up our deep dive into this fascinating world of ordered defect compounds?
I'd like to leave you with this thought.
Today. Okay. Expert speaker, what final thought will you leave me and, of course, our amazing listeners with today?
This whole idea of embracing imperfections, of harnessing defects instead of fearing them, it really challenges us to rethink how we approach material science.
What if, instead of endlessly chasing perfect materials, the key to unlocking even faster, more efficient, and more powerful electronics lies in understanding and controlling these so-called defects?
It's a paradigm shift that could revolutionize the entire field.
It's like we've stumbled upon a secret code, a hidden superpower within the very imperfections we used to dread.
You're telling me the future of our tech might be built on a foundation of organized chaos.
That's mind-blowing.
It really is.
And remember those organized defect structures we talked about in QN5C8?
Yeah.
Imagine discovering similar patterns in other materials.
Unlocking a whole new world of possibilities for electronics.
Wow.
The potential is truly staggering.
It's like those defects were just misunderstood geniuses all along.
Just waiting for someone to recognize their hidden talents. This has been an incredible deep dive. Expert speaker. I don't know about you, but I'm feeling a lot more optimistic about the future of electronics.
That you should.
This is a truly exciting field, and I'm eager to see where this new understanding of defects takes us.
Me too. And I know our listeners are feeling that same sense of wonder.
So to everyone listening, if you're looking for your next deep dive, I highly recommend exploring the world of ordered defect compounds.
It's a fascinating journey into the unexpected side of science, and a reminder that sometimes the most groundbreaking discoveries come from challenging our assumptions and embracing the unconventional.
Beautifully said.
Well, that's all the time we have for today's deep dive into this fascinating world of ordered defect compounds.
We hope you enjoy the journey and learned a thing or two about the surprising power of imperfection. Until next time, keep those minds curious and never stop exploring.